designed by the OpenAI scientists in a way that the hiders can only succeed.
Okay, we're gonna kick it back here
few
since I
million
think we just
rounds,
got
we
disconnected.
start out with pandemonium. Everyone just running around aimlessly. Without proper strategy and semi-random movements, the Seekers are favored and hence win the majority of the games. Nothing to see here. Then, over time, the hiders learn to lock out the Seekers by blocking the doors off with these boxes and started winning consistently. I think the coolest part about this is that the map was deliberately designed by the OpenAI scientists in a way that the hiders can only succeed through collaboration. They cannot win alone, and hence they are forced to learn to work together, which they did quite well. But then, something happened. Did you notice this pointy, doorstop-shaped object? Are you thinking what I'm thinking? Well, probably. And not only that, but about 10 million rounds later, the AI also discovered that it can be pushed near a wall and be used as a ramp, and ta-da! Got him. The Seeker started winning more again. So, the ball is now back on the court of the hiders. Can you defend this? If so, how? Well, these resourceful little critters learned that since there is a little time at the start of the game when the Seekers are frozen, apparently, during this time, they cannot see them, so why not just sneak out, steal the ramp, and lock it away from them?
That's wild.
Absolutely incredible. Look at those happy eyes as they are carrying that ramp. And you think it all ends here? No, not even close. It gets weirder. Much weirder. When playing a different map, a Seeker has noticed that it can use a ramp to climb on the top of a box, and this happens. Do you think couchsurfing is cool? Give me a break. This is box surfing.
Give me a break.
And the scientists were quite surprised by this move, as this was one of the first cases where the Seeker AI seems to have broken the game. What happens here is that the physics system is coded in a way that they are able to move around by exerting force on themselves, but there is no additional check whether they are on the floor or not, because who in their right mind would think about that? As a result,
it'd be murdered by the pot, like found and torn to pieces.
And we are still not done yet. This paper just keeps on giving. A few 100 million rounds later, the hiders learned to separate all the ramps from the boxes. Dear fellow scholars, this is proper box surfing defense. Then, lock down the remaining tools and build a shelter. Note how well rehearsed and executed this strategy is. There is not a second of time left until the Seekers take off. I also love this cheeky move where they set up the shelter right next to the Seekers, and I almost feel like they are saying, yeah, see this here? There's not a single thing you can do about it. In a few isolated cases, other interesting behaviors also emerged. For instance, the hiders learned to exploit the physics system and just chuck the ramp away. After that, the Seekers go, what? What just happened? But don't despair, and at this point, I would also recommend that you hold on to your papers, because there was also a crazy case where a Seeker also learned to abuse a similar physics issue and launch itself exactly onto the top of the hiders. Man, what a paper. This system can be extended and modded for many other tasks too, so expect to see more of these fun experiments in the future. We get to do this for a living, and we are even being paid for this. I can't believe it.
Great video, and it is a really interesting illustration of like emergent intelligence.
As I mentioned, I talked to Sarah Walker, and first of all, she says hi, spoke very highly of you. One of her concerns about physics and physicists and humans is that we may not fully understand the system that we're inside of. Meaning, like, there may be limits to the kind of physics we do in trying to understand the system of which we're part of. So, like, the observer is also the observed. In that sense, it seems like our tools of understanding the world, I mean, this is mostly centered around the questions of what is life, trying to understand the patterns that that are characteristic of life and intelligence, all those kinds of things. We're not using the right tools because
So there's a really great video, I think that Carl Sagan, where he illustrates like how a two-dimensional being would not be able to perceive things in the third dimension. And I guess that's kind of the contention that they're making, is that because we are inside of the number of dimensions that we occupy, we're not actually capable of observing or even conceptualizing those higher level dimensions and having a full, well-rounded understanding of all physics, that we only see it through a very limited prism that we're capable of, and that could be part of the reason why we see so many holes in our understanding of the physical universe.
because we're in the system. Is there something that resonates with you there? It's almost like,
Well, yeah, yes, we do have we have limitations, of course, in the amount of information we can process.
Respect.
On the other hand, we can get help from our silicon friends, and we can get help from all kinds of instruments that make up for our perceptual deficits, and we have to, and we can use, at a conceptual level, we can use different kinds of concepts to address different kinds of questions. So I'm not sure exactly what problem she's talking about.
it's a problem akin to an organism living in a 2D plane trying to understand a three-dimensional world.
Well, we can do that. I mean, you know, we live, in fact, we, you know, for practical purposes, most of our experience is two-dimensional. It's hard to move vertically, and yet we've produced conceptually a three-dimensional symmetry, and in fact, four-dimensional space-time.
Yeah.
So, you know, by thinking in appropriate ways and using instruments and demanding, getting consistent accounts and rich accounts, we find out what concepts are necessary, and I don't see any end in sight of the process or any showstoppers, because let me give you an example. I mean, for instance,
Before he jumps into this, there's just a quick point that I want to make, and this is going back to using like AI as tools for us to understand the universe. So before, he briefly touched on what dark matter is. It is this invisible force that seems to be binding most of the universe together, particularly our galaxy. We know it's there. We can't see it. We can't detect it, and we actually don't know what it is. Recently, scientists were able to find dark matter bridges that may reveal the future or the past of our galaxy. So one of the things that we have these spiral galaxies that seem to have a particular standard of formation, and we see numerous spiral galaxies all throughout the universe. These better understandings of how dark matter helps clump galaxies together will give us a much better fundamental understanding, and okay, this is maybe what it's made of, or why things have the shape that they are, and could give us even better understanding into not just like the Big Bang, but whether or not the universe is going to end with the big crunch or just the big like blackout. Which are both
QCD,
terrifying
theory of
concepts,
strong
by the way.
interaction, has nice equations which I helped to discover.
What's QCD?
Quantum chromodynamics. So it's our theory of the strong interaction, the interaction that is responsible for nuclear physics. So it's the interaction that governs how quarks and gluons interact with each other and make protons and neutrons and all the strong, the related particles, and many things in physics. It's one of the four basic forces of nature as we presently understand it. So we have beautiful equations which we can test in very special circumstances, using at high energies, at accelerators. So we're certain that these equations are correct. You know, prizes are given for it, and so and people try to knock it down and they can't. And
You gotta respect how excited this guy gets about physics and just like the accomplishments that we've been able to make with like things like the Large Hadron Collider and other particle accelerators, and determining, like, you know, they invent this stuff on, well, they don't invent, they, again, I don't know how many of you were around for the beginning of the video, but he had this beautiful thing where he was talking about how a lot of scientists, a lot of it's just guessing. You know, the way that he was describing it was so similar to how you might hear like a musician, like a jazz musician, describe like jamming with their band. It's like we just tried things and we saw what worked and what kind of felt right, and then we played it out, and it worked. That sounds good. That works out. The math is solid. So there's a really interesting symmetry between art and science that you got to appreciate. This guy has a passion for.
But the situations in which we can calculate the consequences of these equations are very limited. So, for instance, no one has been able to demonstrate that this theory, which is built on quarks and gluons, which you don't observe, actually produces protons and neutrons and the things you do observe. This is called the problem of confinement. So no one's been able to prove that analytically in a way that a human can understand. On the other hand, we can take these equations to a computer, to gigantic.
I don't know if you guys know Lex Friedman a whole lot, but what I will say about Lex Friedman is that he does not do anything that he does not emphatically mean and have passion for. The man is driven by the passion for life, the passion for science, the passion for technology, for humanity, for our expansion of consciousness, and for robots. So if he's kissing a robot, goddamn right there's going to be some fucking passion in his heart.
Computers and compute, and by God, you get the world from it.
Guys, please tweet this to Lex Fried. We gotta get Lex. I'd like to see what he thinks of this.
So these equations, in a way that we don't understand in terms of human concepts, we can't do the calculations, but our machines can do them. So with the help of what I like to call our silicon friends and their descendants in the future, we can understand in a different way that allows us to understand more. But I don't think we'll ever, no human is ever going to be able to solve those equations in the same way. But I think that's, you know, when we find limitations to our natural abilities, we can try to find workarounds, and sometimes that's appropriate concepts, sometimes it's appropriate instruments, sometimes it's a combination of the two. But I think it's premature to get defeatist about it. I don't see any logical contradiction or paradox or limitation that will bring this process to a halt.
Well, I think,
you know, that speaking just back to the Lex kissing robots thing, you know, he had Whitney Cummings on his podcast. I believe he was on hers as well. It was hilarious and awkward, and she brought her sex robot. So I'm not saying. Okay, I'm not saying it. I'm just saying.
the idea is
I'm just saying.
to continue thinking outside the box in different directions, meaning just like how the math allows us to think in multiple dimensions outside of our perception system, sort of thinking, coming up with new tools of mathematics or computation or all those kinds of things to take different perspectives on our universe.
Well, I'm
Right.
all for that, and I kind of have even elevated it into a principle, which is of complementarity, following Bohr, that you need different ways of thinking, even about the same things, in order to do justice to their reality and answer different kinds of questions about them. I mean, we've several times alluded to the fact that human beings are hard to understand, and the concepts that you use to understand human beings, if you want to prescribe drugs for them, or see what's going to happen if they move very fast or or are exposed to radiation. And so that requires one kind of thinking that's very physical, based on the fact that the materials that we're made out of. On the other hand, if you want to understand how a person's going to behave in a different kind of situation, you need entirely different concepts from psychology, and there's nothing wrong with that. You can have very different ways of addressing the same.
Okay, does Lex look like he's about to stab him right now? Like he's about to reach over the desk and just like with his pen and just like straight up
material that are useful for different purposes.
Can you describe this idea, which is fascinating, of complementarity a little bit? Sort of, first of all, what state is the principle? What is it? And second of all, what are good examples? Starting from quantum mechanics, you still mentioned psychology. Let's talk about this more. It's like in your new book, one of the most fascinating ideas, actually.
I think it's a wonderful, it's sort of, to me, it's the culminating chapter of the book. And I think since the whole book is about the big lessons or big takeaways from profound understanding of the physical world that we've achieved, including that it's mysterious in some ways, this was the final overarching lesson, complementarity. And it's a approach. It's so unlike some of these other things, which are just facts about the world, like the world is both big and small in different senses, and is big, but we're not small, things we talked about earlier, and the fact that the universe is comprehensible and how complexity could emerge from simplicity. And so those things are, in the broad sense, facts about the world. Complementarity is more an attitude towards the world that is encouraged by the facts about the world. And it's the idea, the concept, of the approach that, or the realization that it can be appropriate and useful and inevitable and unavoidable to use very different descriptions of the same object or the same system or the same situation to answer different kinds of questions that may be very different and even mutually uninterpretable, mutually incomprehensible.
But both correct somehow.
But both correct and sources of different kinds of insight.
Which is so weird.
Yeah, well...
But it seems to work in so many cases.
It works in many cases, and I think it's a deep fact about the world and how we should approach it. Its most rigorous form, where it's actually a theorem, if quantum mechanics is correct, occurs in quantum mechanics, where the primary description of the world is in terms of wave functions. But let's not talk about the world. Let's just talk about a particle, an electron. Okay, it's the primary description of that electron is its wave function, and the wave function can be used to predict where it's going to be.
So I know some people can get hung up on the terminology, and this one tripped me up too. Wave function is essentially referring to the if you think about a musical note, right? It's a wave, and it has a certain amplitude and frequency, right? That sort of determines what we I guess would refer to as the wavelength. And so by looking at physical particles, right, as a function in a wave, so an electron based off of a certain type of amplitude and frequency, we can guess its relative position or its velocity. There's an interesting paradox in quantum mechanics where you can't measure both. You can only measure, I can tell you where an electron is, or I can tell you how fast an electron is going. But I cannot tell you both those two things because because they're actually mutually exclusive. Like, the whole concept of distance is it traveling over two different places. So to give you one coordinate doesn't make sense. Anyway, that's what he's referring to as the wave function is essentially the predictable path of where an electron could be. There's another really great video that I'm going to pull up very quickly while they keep talking.
With different, if you observe, it'll be in different places with different probabilities, or how fast it's moving, and it will also be moving in different ways with different probabilities. That's what quantum mechanics says, and you can predict either set of probabilities. If you know what's going to happen if I make an observation of the position or the velocity.
So when we think about electron, like, this is a great video that's going to illustrate this.
This video for supporting small businesses and for helping people find jobs. More about all that at the end. Atomic orbitals have long been a source of frustration for me. On the one hand, you have simple cartoon diagrams that make them feel friendly, but which are so varied and vague they don't really convey much beyond the basic idea that atoms have a nucleus and some electrons. Some people try to take the cartoony diagrams and make them feel more random or quantum, which is an improvement, but they're still very much just cartoon stand-ins for the vague idea of atom. On the other hand, you have atomic orbitals depicted as fuzzy clouds or balloons or rainbow donuts, which are definitely more technically accurate or technically inspired, but none of which feel like they give me a sense of what's actually going on. Like, what does this blobby thing have to do with orbiting electrons? Is the electron inside it, or on the surface? Why do some of them have blobs and others donuts? And why are some of the donuts rainbow colored? I want to know what an atom looks like, and I want that picture to actually have something to do with the nitty-gritty reality of atoms, since they are indeed real things. You know, like how a diagram of the solar system is both a totally not-to-scale caricature, and yet also represents the very real idea that the planets all orbit the sun in roughly the same plane, and that some are farther out and some are closer in, and if it's animated, we get to see that the closer planets complete their orbits more often. It's a nice picture, and that's what I want for atoms. A good picture. There are a few things I'd like that picture to get across, some of them because they're important for the physics of atoms, and some of them because they're questions my brain wants answers to. Like, where is the electron? How fast is it going? How much energy does it have? How big is this picture relative to other pictures? Of course, the wave-particle nature of quantum mechanics means some of these ideas, like the electron's position, don't translate exactly from our everyday intuition to the atomic scale. But there is a way of thinking about wave-particle duality where you picture the wave function as a bunch of water, and the particle as a speck of dust in that water. The particle is mostly guided by where the water goes, and the water is guided by the equations that determine how water behaves depending on its circumstances. And if you apply the mathematics of that idea to atomic orbitals, and then render it in 3 dimensions, here's what you get.
Yo, this is sick. So this is what it actually might look like.
Beautiful? Here's another.
So when we're talking about the wave function, we are talking about the property of the wave that results in the electrons orbiting the nucleus in these types of patterns. And it's funny, it's kind of what you would see in like a magnetic field or different kinds of like shapes in nature, snowflakes and shit like that. Anyway, back to Frank.
Velocity. But so the wave function gives you ways of doing both of those, but to do it,
yes,
to get
stand on a
those
speaker is
predictions,
another
you have
brilliant
to
one.
process
Yes,
the wave
yes.
function in different ways.
Yes, you
process it one
can
way
like
for position
visualize the
and a
wave
different way
function
for momentum, and those ways are mathematically incompatible. It's like, it's like you have a stone and you can sculpt it into Venus de Milo, or you can sculpt it into David, but you can't do both. You can, and that's an example of complementarity. But to answer different kinds of questions, you have to analyze the system in different ways that are mutually incompatible, but both valid to answer different kinds of questions. So in that case, it's a theorem, but I think it's a much more widespread phenomena that applies to many cases where we can't prove it as a theorem, but it's a piece of wisdom, if you like, and appears to be a very important insight.
Do you?
And if you ignore it, you can get very confused and misguided.
Do you think this is a useful hack for ideas that we don't fully understand, or is this somehow a fundamental property of all or many ideas that you can take multiple perspectives and they're both true?
Well, I think
And
it's both. And,
so it's
that's-
both the answer to all questions.
Yes, that's right. It's not either or, it's both.
It's paralyzing to think that we live in a world that's fundamentally like surrounded by complementary ideas, like because we want we somehow want to attach ourselves to absolute truths, and absolute truths certainly don't like the idea of complementarity.
Yes, Einstein was very uncomfortable with complementarity, and in a broad sense, the famous Bohr-Einstein debates
Or
revolved
box.
around this question of whether the complementarity that is a foundational feature of quantum mechanics as we have it is a permanent feature of the universe and our description of nature. And so far, quantum mechanics wins, and it's gone from triumph to triumph. Whether
Right.
complementarity is rock bottom, I guess you can never be sure. I mean, but it looks awfully good, and it's been very successful, and certainly its complementarity has been extremely useful and fruitful in that domain, including some of Einstein's attempts to challenge it with like the famous Einstein-Podolsky-Rosen experiment turned out to be confirmations of that have been useful in themselves. But so thinking about these things was fruitful, but not in the way that Einstein hoped.
I just realized I muted. Another interesting factoid about Einstein is he didn't believe black holes could exist. He didn't. He even though scientists had approached him with his own equations and said, "Hey, I keep running into this issue of gravitational collapse. I'm following your equations, like what's going on here?" And he sincerely believed that there was some force in nature that would prevent black holes from forming, which obviously is not the case because we know they exist. So Einstein had lots of brilliant ideas, and a lot of his theorems are obviously the foundations for what we understand about the universe and physics today. But it's interesting to hear about some of his contest with his contemporaries.
So as I said, in the case of quantum mechanics and this dilemma or dichotomy between processing the wave function in different ways, it's a theorem. They're mutually incompatible, and that the physical correlate of that is the Heisenberg uncertainty principle. That you can't have position and momentum determined at once. But in other cases, like one that I like to think about or like to point out as an example is free will and determinism. It's
this is going to get interesting. We're wanting a free will
theorem and more a kind of way of thinking about things that I think is reassuring and avoids a lot of unnecessary quarreling and confusion.
The quarreling I'm okay with, and the confusion I'm okay with. I mean, people debate about difficult ideas, but the question is whether it could be almost a fundamental truth.
I think it is a fundamental
that
truth.
Free will is both an illusion and not.
Yes, I think that's correct.
And there's a reason why people say quantum mechanics is weird, and complementarity is a big part of that. To say that our actual whole world is weird, the whole hierarchy of the universe is weird in this kind of particular way, and it's quite profound, but it's also humbling, because it's like we're never going to be on sturdy ground in the way that humans like to be. It's like you have to embrace that.
Well,
this whole thing is like unsteady.
Well,
It's interesting because Lex is kind of addressing this great like divide or this like chasm that people the footing that he would refer to is typically what a lot of human beings found in religion. Religion gave us the ability to understand the world and the way the world was the way it was, why it was the way it was, and why things happened the way they happened. And we had a very solid rooting in that for a very long time. And since now people are, sort of leaving religion, or at least having it take less of a part in their understanding of the fundamental parts of the universe, there's a lot less that we know, and there's a lot less stable footing for us to stand on. So it's a scary pursuit to delve into the deep of the intellectual black hole.
Mess.
it's one of many lessons in humility that we run into in profound understanding of the world. I mean, the Copernican revolution was one. That the Earth is not the center of the universe. Darwinian evolution is another. That humans are not the pinnacle of God's creation. The apparent result of deep understanding of physical reality, that mind emerges from matter, and there's no call on special life forces or souls. These are all lessons in humility, and I actually find complementarity a liberating concept. It's okay,
Yeah, it is in a way.
Is what I remember. There's a story about Dr. Johnson, and he's talking with Boswell, and Boswell they were discussing a sermon that they both heard, and the sort of culmination of the sermon was the speaker saying, "I accept the universe," and Dr. Johnson said, "Well, you damn well better." and there's a certain joy in accepting the universe because it's mind expanding, and and to me, complementarity also suggests tolerance, suggests opportunities for understanding understanding things in different ways that add to rather than detract from understanding. So I think it's an opportunity for mind expansion, and demanding that there's only one way to think about things can be very limiting.
On the free will one, that's a trippy one, though. To think like I am the decider of my own actions, and at the same time I'm not, is tricky to think about. But there does seem to be some kind of profound truth in that.
I think it is tied up. It will turn out to be tied up when we understand things better with these issues of self-awareness and where we get what we perceive as making choices. What does that really mean, and what's going on under the hood? But I'm speculating about a future understanding that's not in place at present.
Your sense there will always be like, as you dig into the self-awareness thing, there'll always be some places where complementarity is going to show up.
Oh, definitely. Yeah. I mean, there will be, how should I say? There'll be kind of a God's eye view, which sees everything that's going on in the computer or the brain. And then there's the brain's own view, or the central processor, or whatever it is. What we call the self, the consciousness, that's only aware of a very small part of it, and those are very different. Those are so the God's eye view can be deterministic, while the self view sees free will. And I'm pretty sure that's how it's going to work out, actually. But as it stands, free will is a concept that we definitely at least I feel I definitely experience. I can choose to do one thing than another, and other people I think are sufficiently similar to me that I trust that they feel the same way. Uh, and it's an essential concept in psychology and law and so forth. But at the same time, I think that mind emerges from matter, and that there's an alternative description of matter that's up to subtleties about quantum mechanics, which I don't think are relevant here, really is deterministic.
Let me ask you about some particles.
Okay.
First, the absurd question, almost like a question that like Plato would ask. What is the smallest thing in the universe?
As far as we know, the fundamental particles out of which we build our most successful description of nature are points. They have zero. They don't have any internal structure. So that's as small as can be. So what does that mean operationally? That means that they obey equations that describe entities that are singular concentrations of energy, momentum, angular momentum, the things that particles have, but localized at individual points. Now, that mathematical structure is only revealed partially in the world, because to process the wave function in a way that accesses information about the precise position of things, you have to apply a lot of energy, and that's not, that's an idealization that you can apply infinite amount of energy to determine a precise position. But at the mathematical level, we build the world out of particles that are points.
So do they actually exist, and what are we talking about? So like,
they exist.
So let me ask, sort of, do quarks exist?
Yes. Do electrons exist? Yes. Do photons exist? Yes.
But what does it mean for them to exist?
Okay. So, well, the hard answer to that, the precise answer, is that we construct the world out of equations that contain entities that are reproducible, that exist in vast numbers throughout the universe, that have definite properties of mass, spin, and a few others that we call electrons. And what an electron is defined by the equations that it satisfies theoretically, and we find that there are many, many exemplars of that entity in the physical world. So in the case of electrons, we can isolate them and study them in individual ones in great detail. We can check that they all actually are identical, and that's why chemistry works. And yes, so that in that case, it's very tangible. Similarly with photons, you can study them individually, the units of light, and nowadays it's very practical to study individual photons and determine their spin and their other basic properties, and check out the equations in great detail. For quarks and gluons, which are the other two main ingredients of our model of matter that's so successful, it's a little more complicated, because the quarks and gluons that appear in our equations don't appear directly as particles you can isolate and study individually. They always occur within what are called bound states, or structures like protons. A proton, roughly speaking, is composed of 3 quarks and a lot of gluons. But we can detect them in a remarkably direct way, actually, nowadays. Whereas at relatively low energies, the behavior of quarks is complicated. At high energies, they can propagate through space relatively freely for a while, and we can see their tracks. So ultimately, they get recaptured into protons and other mesons and funny things. But for a short time, they propagate freely, and while that happens, we can take snapshots and see their manifestations. This is actually, this kind of thing is exactly what I got the Nobel Prize for, predicting that this would work. And similarly for gluons, although you can't isolate them as individual particles and study them in the same way we study electrons, say, you can use them theoretically as entities out of which you build tangible tangible things that we actually do observe. But also you can, at accelerators at high energy, you can liberate them for brief periods of time and study how they, and get convincing evidence that they leave tracks, and you can get convincing evidence that they were there and have the properties that we wanted them to have.
Can we talk about asymptotic freedom, this very idea that you won the Nobel Prize for?
Yeah.
So it describes a very weird effect to me. The weird in the following way. So the the way I think of most forces or interactions, the closer you are, the stronger the effect, the stronger the force.
Yeah.
Right? With quarks, the closer they are, the less so the strong interaction.
Yeah.
And in fact, they basically act like free particles when they're very close.
That's right.
So just to give you guys like a quick visualization, when he was mentioning using particle accelerators and colliders to visualize quarks and different particles, here are a couple of images of the type of data that you get from the output of a particle accelerator. So this is where all of these different lines of data are essentially compiled based off of the different sensors that collect this data when they mash whatever particles of whatever together. You can see some consistency in how these look. It looks literally like an explosion, right? And scientists are able to distill and discern the types of particles, their behavior, why they're doing something, because it gives us an insight into their properties. So just a little bit of a visualization about what they're talking about here.
Right. Yes.
Well, but this requires a huge amount of energy. Like, can you describe me how does this even work?
Well,
how weird it is?
A proper description must bring in quantum mechanics and relativity, and it's so a proper description and equations. So a proper description really is probably more than we have time for, and would require quite a bit of patience on your part. But
Well, how does relativity come into play? Wait a minute.
Oh, relativity is important because when we talk about trying to think about short distances, we have to think about very large momenta, and very large momenta are connected to very large energy in relativity. And so the connection between how things behave at short distances and how things behave at high energy really is connected through relativity in sort of a slightly backhanded way. Quantum mechanics indicates that to analyze short distances, you need to bring in probes that carry a lot of momentum. This again is related to uncertainty, because it's the fact that you have to bring in a lot of momentum that interferes with the possibility of determining position and momentum at the same time. If you want to determine position, you have to use instruments that bring in a lot of momentum. And because of that, those same instruments can't also measure momentum because they're disturbing the momentum. And then the momentum brings in energy. And yeah. So that there's also the effect that asymptotic freedom comes from the possibility of spontaneously making quarks and gluons for short amounts of time that fluctuate into existence and out of existence, and the fact that that can be done with a very little amount of energy, and uncertainty in energy translates into uncertainty in time. So if you do that for a short time, you can do that. Well, it's all comes in a package, and you can. So I told you it would take a while to really explain, but the results can be understood. I mean, we can state the results pretty simply, I think. So in everyday life, we do encounter some forces that increase with distance and kind of turn off at short distances. That's the way rubber bands work, if you think about it. Or if you pull them hard, they resist, but they get flabby if the rubber band is not pulled. And so that can happen in the physical world. But what's really difficult is to see how that could be a fundamental force that's consistent with everything else we know. And that's what asymptotic freedom is. It says that there's a very particular kind of fundamental force that involves special particles called gluons with very special properties that enables that kind of behavior. So there were at the time we did our work, there were experimental indications that quarks and gluons did have this kind of property, but there were no equations that were capable of capturing it. And we found the equations and showed how they work, and showed that they were basically unique. And this led to a complete theory of how the strong interaction works, which is the quantum chromodynamics we mentioned earlier. And so that's the phenomenon that quarks and gluons interact very, very weakly when they're close together. That's connected through relativity with the fact that they also interact very, very weakly at high energies. So at high energies, the simplicity of the fundamental interaction gets revealed. At the time we did our work, the clues were very subtle, but nowadays at what are now high energy accelerators, it's all obvious. So we would have had somebody would have had a much easier time 20 years later looking at the data. You can sort of see the quarks and gluons. As I mentioned, they leave these short tracks that it would have been much, much easier. But from indirect clues, we were able to piece together enough to make that behavior a prediction rather than a post-diction, right?
So it becomes obvious at high energies.
It becomes very obvious. When we first did this work, it was frontiers of high energy physics, and at big international conferences, there would always be sessions on testing QCD and whether this proposed description of the strong interaction was in fact correct, and so forth. And it was very exciting. There were but nowadays, the same kind of work, but much more precise, with calculations to more accuracy and experiments that are much more precise, and comparisons that are very precise. Now it's called calculating backgrounds, because people take this for granted and want to see deviations from the theory, which would be the new discoveries.
Yeah, the cutting edge becomes the foundation. The foundation becomes boring. Yes.
Yeah.
Is there some, for basic explanation purposes, is there something to be said about strong interactions in the context of the strong nuclear force for the attraction between protons and neutrons, versus the interaction between quarks within protons?
Yeah.
And so on?
Well, quarks and gluons have the same relation basically to nuclear physics as electrons and photons have to atomic and molecular physics. So
Interesting. There's
atoms
a symmetry there.
and photons are the dynamic entities that really come into play in chemistry and atomic physics. Of course, you have to have the atomic nuclei, but those are small and relatively inert, really the dynamical part. And for most purposes of chemistry, you just say you have this tiny little nucleus, which QCD gives you. Don't worry about it. Just it's there. The real action is the electrons moving around and exchanging and things like but we wanted to understand the nucleus too, and
I think this guy is on mushrooms, for those who were asking earlier.
Quantum mechanical clouds of electrons held together by electrical forces, which is photons, and then this radiation, which is also another aspect of photons.
That's where all the fun happens, is the electrons and the photons.
Yeah,
and all that kind of
that's
stuff.
right. And the nucleus are kind of well, they're necessary. They give the positive charge and most of the mass of matter, but they don't, since they're so heavy, they don't move very much in chemistry, and I'm oversimplifying drastically.
They're not contributing much to the interaction in chemistry.
For most purposes in chemistry, you can just idealize them as concentrations of positive mass and charge that are you don't have to look inside, but people are curious what's inside, what really, and that was a big thing on the agenda of 20th century physics, starting with the 20th century and unfolding throughout, of trying to understand what forces held the atomic nucleus together, what it was, and so. Anyway, the story that emerges from QCD is that, very similar to the way that, well, broadly similar to the way that clouds of electrons held together by electrical forces give you atoms and ultimately molecules. Protons and neutrons are like atoms made now out of quark clouds held together by gluons, which are like the photons that give the electric forces, but this is giving a different force, the strong force, and the residual forces between protons and neutrons that are left over from their basic binding are like the residual forces between atoms that give molecules, but in the case of protons and neutrons, it gives you atomic nuclei.
So again, for definitional purposes, QCD, quantum chromodynamics, is basically the physics of strong interaction.
Yeah, we understand. We now would understand. I think most physicists would say it's the theory of quarks and gluons and how they interact.
So similar to how, like, the we look at the atomic structure, we look at it as protons, neutrons, and electrons. The internals of those are your quarks and your gluons. Guys, we've been going for about 2.5 hours here, and I think I'm going to start wrapping up the stream. It has been a real pleasure hanging with friends, talking about physics. I think next Tuesday we'll kind of pick things up where we left off with this conversation, and then funnel into some other cool stuff that I was looking forward to talking to. Thanks for sticking around for as long as you guys did, and don't forget to, keep checking in and saying hello. I'll catch you guys on the flip side.